This is my screencast assignment for Conceptual Objective 5D. I had to explain what I did wrong on my quiz and then fix all the problems I had. So for the first problem, this is the problem with this picture. So according to what you wrote down, and I accidentally used the whole weight of the Earth in the formula because I didn't draw it straight down. Instead, I just drew it perpendicular with the box, and it should really go straight down. Only the force normal goes perpendicular. So if I just change that number, I come up with the right answer. So then I changed my free body diagram. So I drew the weight of the Earth going down, and then I calculated the weight of the Earth, which is actually the same as before, but I just had to use a different part of it. So the weight of the Earth is just the 2 kilogram box times 9.81, which comes out to be 19.62 newtons. So then for the answer, I used the sum of the forces in the x direction equals the spring constant times the change in length in the x direction, because it's going from left to right. So it wants to know how far the block slides down the incline, down that incline. So I did on the right hand side, nothing really changes. So on the left hand side, all the forces in the x direction are just the component of the weight. So that's right here. It's the only one in the x direction, and this is the y, and that's the y. So we only need the x. So instead of using the entire weight that I used before, the 19.62 newtons, I just had to use this bottom portion, which is 19.62 newtons, which is the weight of the Earth, times the sine of 37 degrees will give me the magnitude of that force. So that is what you get on the left side, and then the right side you just bring down the entire way, and you're trying to solve for the change in L. So it gives you the constant to be 100 newtons divided by meters. So plugging in what I told you before and then the 100, you just divide this number by the 100, and then you end up getting 0.12 meters down the ramp, or down the incline, for the change in L. And then for the second problem, this is a problem, and then the only thing I did wrong was made a copying error in this 80 newtons over here. I wrote 8 instead, so I just fixed that, and I fixed my work and said 80 newtons equals 400 newton meters, and then, or newton divided by meters, and then that multiplies by the change in L final, because the initial gets knocked out, and then so the final length is equal to 0.2 meters instead of 0.02 meters. For the third question, this is a question, and then it wants to know what is the magnitude of the force of the track on the car at the bottom of the dip, and then that's the picture. So I drew a new, or this is actually my original free body diagram. So I don't really know what I did wrong because I don't remember. I either didn't know how to do it because I stopped here, or I ran out of time or something. So this is my original free body diagram. It's actually correct. I just didn't do anything with the work. So the physical principle was fixing the problem. Physical principle was centripetal acceleration in Newton's second law. So the sum of the forces in the y direction equals m times the acceleration in the y direction. Then, since acceleration, it's accelerating in the y direction because of centripetal, so since the roller coaster's at the bottom of this loop right here, the acceleration is going to be heading towards the center. So because of that, that's how you know the acceleration in the y direction is an actual value. So m times ay, and then the ay is just centripetal, so you plug in the v squared over r, and then that just goes all the way down the formula. But on the left hand side, the forces in the y direction are the force normal, which you're trying to solve for, and then the weight of the earth going straight down. So if you do the force normal, because the y going up is positive y direction and down is negative, so force normal is going up, and you subtract it by the weight of the earth acting on the roller coaster, and then you bring down that m times v squared over r, then bringing it down and solving for force normal, which is the force of the track on the car, is that formula right here. So then plugging in what I know, the mass is 500 kilograms, then the velocity it gave us was 16 meters per second, and then you square that and you divide it by 40 meters, which is the radius of that picture right there. And then you add gravity. I took out the mass, so that just goes out in front. Then you add the gravity to this value. So then you come up with 8,105 newtons as the force normal, or the force of the track on the car at the bottom of the dip. For the fourth question, I was just completely wrong. Being able to figure out the question before that would have definitely helped me, because that I immediately knew what the answer was as soon as I got that question. So I originally said equal to, which is wrong. The answer, or at least I said the answer was, I fixed it and said the answer is less than. And the question asks, is the normal force exerted on the skateboarder by the bump greater than, less than, or equal to the weight of the skateboarder? And then this picture, and the skateboard is going 5 meters per second. So I said less than because, like the question before, some of the forces in the y direction, and then simplified. It's the same simplification as the other question. So I said it's less than because the weight has to be supplying a larger force, because otherwise the skateboarder would have skated into the air. So in this problem, the weight plus the mass and the centripetal acceleration equals the force normal. So if it's asking about the force exerted on the skateboarder, so the force exerted on the skateboarder by the bump has to be less than the bump acting on the skateboarder, because the skateboarder acting on the bump would be, the skateboarder by the bump would be less than the skateboarder acting on the bump, because if the skateboarder acting on the bump was greater, then that means the skateboarder would go into the air. So the force exerted on the skateboarder by the bump has to be less, because that's what makes the skateboarder stay on the ground or on the bump. So then it asks it to relate it to the weight of the skateboarder. So it's almost better just to explain it that the force exerted on the skateboarder by the bump has to be less, because if the weight if the weight of the skateboarder, well, it has to be less than the weight of the skateboarder, because if the weight of the skateboarder was more, or less, sorry, if the weight of the skateboarder was less, then that means, that's another way to say that the skateboarder is going in the air, which is what I kind of wrote right here. So the end answer is just that the force exerted on the skateboarder by the bump is less than the weight of the skateboarder on the bump. And then for the bottom question, I actually didn't finish this one, so this was my work on the left hand side that I had. So I originally picked the answer A and I just didn't finish it, so I'm sticking to my answer A, but I have the work for it here. So I used the sum of the forces in the y direction equals m times ay, and the ay is the centripetal acceleration, so you plug in the v squared over r. And then same as I've been doing, the force normal minus the weight of the earth equals mass times the centripetal acceleration. And that's just because this free body diagram over here is just those two forces. And then it's going around this circular half circle turn. So then once you bring the weight over, you can take out the mass. You can take it out in front. So I actually think I should have left the mass in there now that I'm looking at it. I can't really explain why I crossed that off, but either way, I got, if you do cross off the mass, I got 9.81 plus the 100 squared, which is the velocity they gave us, and then 400 meters was the radius that was given. And then if I had left the mass in there and just multiplied it out, it would have just came up with a slightly larger force normal, but it doesn't change my answer at all. So then after that, I did the sum of the forces in the x direction, because you're trying to see if it went into the walls or not. So wanted to know if it hit the wall or hit which wall or stayed in the center. So we really care about the x direction, so the sum of the forces in the x direction equals mass times acceleration in the x direction. So the force friction, it told you that there was a force of static friction, and then the coefficient for that was 1.1. So you know in the x direction there's going to be, well, there's something propelling the car, but you don't really know what that is. So the only forces in that direction is that force friction, and so that's going to be on the left hand side. And then on the right hand side is the right hand side is just going to be mass times v squared over r. So simplifying the left, you get the lambda times force normal is the force friction, and on the right hand side you just bring it down. So the coefficient of static friction they gave us was 1.1, and then the force normal is 34.81 newtons, and that was just the force normal I found up here, which could have been, I think it should be a slightly higher number, but doesn't change my answers again. So that's on the left hand side, and then on the right hand side is just mass times v squared over r. So doing 100 squared over 400 squared, or 400 meters, you take this number on the left and divide it by this number on the right, then you get mass equals 1.53164 kilograms, and that comes out to be 1,531 grams. And it asks about a race car, and for the mass to come out to be that value is a really small weight or mass for a race car, and that's kind of not believable. So I said because that mass is so small, that the mass, that obviously means that the car is going too fast. So I just said the car is going too fast for the curve. So if it's going too fast, the car is just going to crash into the outer wall, which is A for my final answer. And then that was the end of the quiz.